Welcome everybody to our today's TransferLab seminar. The TransferLab seminar is part of the Applied AI Institute for Europe, which is a non-profit organization dedicated to advance AI in Europe. And our seminar is a platform where researchers and engineers share recent advances in AI and machine learning. And in particular at TransferLab, we are working on topics like reinforcement learning, data evaluation, simulation and AI, and probabilistic modeling. And today we have an external speaker. It's Tom Schierenbeck from the University of Bremen. Dominic has made the contact, and I will hand over to him in a minute.
It's my pleasure to introduce to you Tom Schierenbeck as today's speaker. Tom is a PhD student at the Institute for Artificial Intelligence at the University of Bremen. And I believe we have at least two things in common. The first is presumably a passion for probabilistic models. And the second is our PhD advisor, Professor Michael Beetz. And Tom's research interests range from probabilistic models and robotics to databases and software engineering, so quite varied. And he's involved in a number of research projects. The first is called PyCram, which is concerned with the re-implementation of the common Lisp-based cognitive robot abstract machine, or CRAM. And the goal of this project is ultimately to facilitate the development of cognition-enabled robot control programs. Another project he's involved in is FAME, a future-oriented cognitive action modeling engine, where one of the goals is to learn robot plans from video demonstrations. And last but not least, he's involved in the joint probability trees project, and more generally, probabilistic modeling. And he will now tell us more about this.
Yeah, thanks for the kind introduction. Today I'm going to tell a bit about probabilistic machine learning. I figured out that from now you are already also interested in probabilistic machine learning, so perhaps some of this may seem familiar to you. So Dominic has already introduced me. I'm here as a substitute for Daniel Niger, who invented that model that we are going to discuss today, and we see him on the left here. And yeah, I'm, so to speak, his apprentice. I learned a lot from him. He is now off in his own company, and I'm left here and continue his work. Yeah, Dominic already told the project that I'm interested in, so here are some references if you are interested. About the Institute for Artificial Intelligence, here we do a lot of AI-powered and cognition-enabled robotics. That means we want to mix the traditional tools of artificial intelligence with the modern machine learning approaches to achieve household tasks. So we want robots to do everyday activities for us, like cooking, cleaning, picking up stuff, the boring things we don't want to do at home. We have different fields in this institute. One is perception, the other is reasoning, learning, knowledge decision-making, also using ontologies, prospection, and classical planning. We do propose the cognitive robot architecture CRAM or PyCram in the newer days, where we control robot agents using a very easy to use language such that almost everyone can write a simple robot program that makes a robot do complicated things. We also have open education, research, and innovation, so all our work, all our teaching can be found online, and if you are interested, you can just read it up there or talk to the people here. And we already built some successful robot applications. I think the most famous demonstration is the popcorn cooking demonstration of the PR2, where he makes popcorn at some conference. So the goals of today is to learn what is probabilistic machine learning, which classes exist inside probabilistic machine learning, how models have to be designed to match certain requirements, and then about Daniel Niger's work, so what are the Niger distributions and what are joint probability trees. Probabilistic machine learning. So probabilistic machine learning is, as the name suggests, a subfield of machine learning and artificial intelligence. And as that's pretty cool because we already figured out with classical machine learning that it's a key tool to automate tasks where it's just too gritty to write the code yourself. So you need a machine to write the code for you. In probabilistic machine learning, we express the uncertainty of answers of problems explicitly, instead of just providing facts like this is definitely a dog. We would say this is with a probability a dog and with some probability some other thing. And that is a cool thing to do because, especially in perception in convoluted areas, one is quite not certain what do we see here, and it would be more beneficial for a rational agent to maintain these beliefs and not just discard them and go for the current mode. The answers in probabilistic machine learning are either probabilities or entire distributions about all the facts that may be. And this is cool because it allows reasoning over every possible scenario and not just about the thing the agent believes the most right now. So provocative example on why traditional machine learning is not enough. In most modern machine learning algorithms, we formulate a model that calculates the conditional expectation over our target given some observed values. On the right, we see a normal distribution where it was conditioned on not being in the interval from -1 to 1. And we can see that we get like this symmetric shape of truncated normal distributions, and that a machine learning algorithm would still answer that the conditional expectation of that distribution is 0, even though we just said that 0 is definitely not in the things we want to have. And from this idea that answers are more complicated than just single numbers or single classes or classes of probabilities, we get that for such simple things like Gaussian distribution, it's already not enough to just say the answer is the expectation. We need more complicated tools. And today we will investigate how to build such tools, what are the requirements for such tools, and what price do we pay. So formalize the quantities of interest in probabilistic machine learning are the evaluation of the likelihood function, so the density of a point at every point, then the computation of integrals over hyperrectangles. That means if we have a set of independent constraints, so to speak, or an axis-aligned bounding box in very high dimensions for the computer vision enthusiasts, for example, x is between 1 and 2 and y is between 3 and 4, that would be the definition of a hyperrectangle. We want to integrate over that described area our density function. So integration is a key tool is the key tool to probabilistic machine learning. Furthermore, we are interested in moments, just as we saw the first moment on the other slide, the expectation. And we are most of the time also interested in the variance and in very rare cases also in higher order moments, but these are the most known moments that are interesting. And of course, finding the mode of a distribution. So what is the most likely configuration of our random vector in the entire distribution, or perhaps under some condition. Achieving this integration calculations is complicated, and the price we pay is heavy. So traditional machine learning, we usually want to optimize a problem. We want to maximize expected return or something. Here we want to calculate certain integrals, and the integration of any function is not possible. So we starkly have to restrict the functions we can form and we can calculate on. And we are most of the time interested in creating models that can compute every integral of interest and not just one integral or two integrals. And in 2020, such constraints on functions have been formalized in the first resource that I linked there. And yeah, we are now going to have a very brief and short introduction on what that means, what is integratable of a function. So the family of probability distributions is called probabilistic circuits, where we have efficient integration available. And the probabilistic circuits are a dialectic acyclic graph, just like Bayesian networks, for example. But the nodes in that graph are either tractable distribution over an input unit. So these are like the base distributions where we know closed forms of, like the univariate Gaussians or the univariate uniform distribution or the Poisson distribution, whatever you want. And then you could either have a product over subsets of another circuit, so you have a product of different distributions, or you have a convex weighted sum of distributions. So convex just means all weights are positive and the weights sum to 1. An example would be on the left, we would see that we have some Gaussian input units, and then we are summing them together to form a Gaussian mixture. And then we are multiplying them to form multivariate distributions. And then we are having mixtures of these multiplications, and so on until we have a complex enough structure to accurately represent our distributions. For most people, they only know graphical models. So I have on the right an example on how we could express a graphical model in a probabilistic circuit. So on the right top corner, we have the naive Bayes, the Gaussian, the Bayesian network of a naive Bayes classifier, where we just say, given y, everything is independent. And then we could reformulate that as a circuit where we would say, okay, now to form the integral of that, we would sum over all cases of y, and then just multiply a, b, and c together with the certain value of y. Is that clear to everyone so far? Good. Tractable inference, so this is now just a description of we summed and multiplied something, but what do we have to sum, and when can we multiply, and when is the integral and the mode still preserved? So there are two key definitions in the work from 2020. The first is the decomposability definition. A product node is decomposable if the scopes of its input units do not share variables. That means if I just multiply two functions together that do not share variables, then if I want to integrate that, I can integrate these functions independently of each other and do not have to apply the product rule of integrals, which is very messy to calculate. So this is one way to make things easily calculatable. And for a PC, so for the entire circuit, we say it's decomposable if all of its product units are decomposable. For sum nodes, a sum node is deterministic. For any fully instantiated input, the output of at most one of its children is non-zero. So the left condition is enough to prove that integrals are computable. And the right statement that supports have to be disjoint, or the fully instantiated input densities have to be disjoint, means basically that if I have a sum of other distributions, they must not intersect. So when I want to find the mode of the distribution, then I can just take the mode, the max of the mode of the subcircuits. There's a more complicated proof to that, but I will spare you this because we are in an applied institute and not in a mathematical institute. So yeah, just remember we have to make some disjoint calculations here. And that's why that is already the reasons why I don't like Gaussian distributions. Gaussian distributions, a mixture of Gaussian distributions can never be disjoint because they have infinite support and therefore infinities intersect. So now let's dive into application of what does that mean. I've prepared it live, so it's cooler. So the first distribution we are going to investigate is the so-called Niger distribution. At least I teach it that way, and I name it that way because Daniel came up with it so Daniel Niger, the one who should have given this presentation, and he came up with that. And the idea of that distribution is so smart and yet so simple. And actually, back in the day, a bit of story time, when Daniel admitted that he didn't even know about the conditions that we need for tractable calculations, for calculations in linear time. But he just thought, yeah, this is a good way, and this is exactly what I need. So we will try to rethink what he thought and look at the result. So in applied problems, you usually don't get data and likelihoods to them because the likelihood of the data is unknown. We don't know how probable are the scenarios, but we want to estimate that. So most of us have seen code like that. Okay, we generate some random data here, and in this case, we just generate random data from a mixture of two Gaussian distributions, where the one is with mean 0, standard deviation 1, and the other with 5 and out of 5. And we just draw 1,000 samples from each. And then we get the data frame with a lot of samples. So the idea is that we now create a mixture of uniform distributions that will approximate the shape of the distribution where our data is from, which is unknown. So we cannot just say, oh, I know this is a mixture of Gaussians, because in reality, we don't know. We don't know how the shape of the distribution looks like. And we now want to find that out. We can formulate that as a maximum likelihood problem, and formulating things as a maximum likelihood problem is great, because maximum likelihood is exactly what our machine learning models should optimize. So let's say we formulate the average likelihood of our data by just summing up the likelihood of every point and dividing by the number of points. That is just very standard average definition. And then we now think that we want to split the data into two disjoint subsets at certain points. Sorry. So let's call these partitions of the data d left and d right. D left for everything that is smaller than the point, and d right for everything that is greater or equal to the point. And then we can calculate the split value by just taking the distance maximizing split, so just the average between the two border points, so to say. Now we assume that each split is uniform distributed, and we calculate for every split how much does the likelihood of our data increase if we add new uniform distributions here. And that is already the magic behind it, and then we just do that recursively until we have achieved a high enough likelihood, or do not improve in likelihood anymore, or think that we have too many uniform distributions already, and that we shouldn't create anymore. So the math of that is very straightforward. You can, this is all online available via the link that I have when you click on the slide that I just showed, but I don't know where it is. And so let's just look into the result. So if we just say, okay, we take our Niga distribution over a continuous random variable x, and I say I want 50 samples in each quantile at least, and I want at least a likelihood improvement of 1% of 0.1%. Then I fit the distribution, and I get a distribution that looks like that. So this already looks very, very close to a mixture of two Gaussian distributions without ever specifying that it's a mixture of Gaussian distribution. We just got data in, and we got this thing out. Due to the partitioning property of selecting the splits, we also have a distribution where we can calculate the mode easily, because we just check which of these distributions has the highest value and then take that as a mode. We can see that on the right here that this is the mode of the distribution, and it is between 4.97 and 4.88, so pretty close to the actual mode of a Gaussian mixture, which in turn is not really calculatable because it's an optimization problem, but we could imagine that the mode is kind of around here. If we compare that to the real distribution we sampled from, so let's just say we know that distribution, it's a Gaussian mixture with uniform weights and the standard variances and means from above, we see that our approximation is so close that we cannot distinguish the CDFs anymore. In blue, we see the Gaussian CDFs, and in red, we see the Niga distribution CDF, so the integral. And we see they are almost the same. And in orange, we see the original PDF, so the distribution, the mixture PDF, and in blue, the learned PDF. And we can see it's kind of the same line. The one is discretized in a interesting way, and the other is just continuous. And we see that the expectation in the middle here is at the pretty much exact same spot. It is a deviation between 0.41 and 0.05, so very close. And if we go back, is that not working? So, oh, okay, let me just reload that. Now it's also in white. That's better for the eyes. Then we see that we couldn't calculate the exact mode, but the Niga distributions mode is approximately where we could, with our eyes, see the mode of this distribution. So already a pretty genius tool to just approximate any PDF. are there questions so far? Because the next step is just doing that in a bigger fashion. The multivariate case, how does this scale to dimensions? So historically speaking, Daniel thought, what if a decision tree, what if we have a decision tree and we start taking away features from them? So let's say I have 5 variables and I learn my decision tree based on those 5 variables. And now I just say, okay, you cannot use that variable anymore to decide something. Mathematically speaking, this would be similar to marginalizing the decision tree. And so he came up with, okay, with the statement that we could just form distributions in the leaf of decision trees and then say, okay, now marginalization is a defined thing to do, and we can just go ahead and do it. That is a short story of what happened, and the algorithm behind this, I don't know why is it. Oh, perhaps if I just rerun everything. Okay, the math is now still a bit blank, but essentially what he came up with is that we just do the C4-5 algorithm. That means minimizing the impurity of the partitions we obtain by splitting on any dimension. And in the continuous case, that means minimizing variance, and in the discrete case, in the symbolic case, that means minimizing entropy. And then we just seek on every axis an axis-aligned split that minimizes the entropy of every variable. And yeah, that is essentially the decision tree algorithm, but for multiple dimensions. And if we now go ahead and sample from a mixture of multivariate Gaussians, we could obtain sample sets like these. That looks, most of us will know distributions like that. So here's just an overloading of the definition of the learning algorithm so we can see what it does. So if we now look in the, can I make it bigger? No. Shouldn't have done that. Okay, if we now look at the data set, we see that the green line here splits the data into 2 disjoint subsets such that the variance of all dimensions is reduced maximally. Then we just do that over and over again. So next is the purple line as the decision criterion. Then we take the orange line here for deciding next, and then we take the blue line here, and then the pink line here, and then the green line here. And then we obtain partitions of the data set where we can assume that the dimensions are independent. So we can just fit a fully decomposed product unit to it in probabilistic terms and just multiply the distributions in the leaves. And then we get a sum of product units. And essentially, that sum is also deterministic because the algorithm divides the data into disjoint partitions. So obviously, the PDFs will be disjoint, and therefore we can also efficiently maximize it. If we look at the leaves that are learned, so the components of the overall multivariate distributions that are created, we see that all of them look like parts of a multivariate Gaussian, but of course we cannot express the change of variables that a multivariate Gaussian expresses, so we approximate it by just creating a complex enough mixture of set distributions. And due to the model freeness of Niger distributions, it doesn't really matter where we split because we can approximate the shape of the distribution in that domain anyway. Yeah. And yeah, and that results in fairly complex multivariate distributions that are competitive with gradient descent approaches or general deep learning approaches of probability methods in terms of likelihood. So the likelihood of a joint probability tree, which is this, is close to the likelihood of a complex model, but we get the benefit of exact calculations. Go back to the presentation. Where's my presentation? Here. Okay. So the next concept of that is to define dynamic models on these joint probability trees or general on circuits. So we already know from hidden Markov models that reasoning over dynamic worlds is a pretty important concept because unfortunately the real world is dynamic and we have to reason about the real world and not some made up world. Hidden Markov models use Bayesian networks for that. So we just define emission model, a transition model, and starting space, and that's it. Then we just have a Bayesian network and we can calculate over that. However, complexity of graphical models is exponentially heavy in their bounded tree width. So the closer they are to a tree, in a graphical sense, the faster the inference is. And that is a problem because we have a fixed number of variables. And if we want to express certain things, we have to get rid of the tree property because the tree only allows n-1 interactions with n is the number of nodes. And that is problematic. The shallow form of JPTs, so we have the sum of something else, allows them to also be used for template models without ever explicitly defining the hidden variable. In a hidden Markov model, you would have to define, let's say, words or something as hidden variable, and then you would have to define how many words are there. JPTs do not need to do that. They can just define anything there or find out what it actually is and then do it like that. Before we get to the point, let's see an example of that. So let's first look at the right. There's a hidden Markov model where x is a hidden variable, and then we create that into a circuit. So just as in the Bayesian and the naive Bayes, we would have a sum unit for the root of that Bayesian network. So x1 is the root in green. And then we would say, okay, we have to multiply the probability of the root with the probability of the first leaf of the root, so y1 given that state of the root, and then y1 given the other state of the root. And then we get like cycles in our computational graph, but not in our dependency graph. And that's why this is still a tractable circuit. So then we just do that for the second time step, for the third time step. And we could just imagine that we increase the length of the circuit line there with increasing time steps. If we look on the left, we see on the left the equation for mixture models is just the weighted sum of some other distributions. And the latent variable interpretation of a mixture is that we can use the index set of these weights as a random variable. You have seen that perhaps in Bayesian deep learning or something, that we just say, okay, this parameter is now a variable and not just a parameter anymore. And then we can express any mixture model as a Bayesian network. So we just say, okay, this latent mixture variable is now I, and we just say, given the component we are in, given the mixture index, we can calculate our x. If we look at JPTs, we have this form that it's also a mixture of some other distribution, and in this case, fully factorized distributions, so particularly easy distributions. And we can just say, in a blunt term, JPTs come up with a new hidden random variable that they make up that explains conditionally independent partitions of your data. We said that determinism is given when, or efficient mode calculation is given when your variables are, your supports of distributions are disjoint. So if we marginalize a JPT, we perhaps destroy the determinism property. However, JPTs can be forced to be marginally deterministic. So after marginalization of certain variables, they are still deterministic. But due to time constraints and also scope constraints of this lecture, we will not go into that. So the question is what's coming next? Probabilistic circuits in template models, obviously, because that's what we just discovered. That's possible. And I've already written a demo for that, but I'm still working on a bedtime implementation because my implementation of that now is low usability on the user end side. And I want more like high usability there. So that's what's coming next. Then SQL as a query language for probabilistic circuits. Dominic already said that I'm interested in databases, and databases are actually a Monte Carlo simulation of some stochastic process. So that's why I'm interested in them. It's just another way to calculate probabilities. And I would like to use the same query language for that. Then a large-scale evaluation on template JPTs with Pygram. So in our planning language for the robots, we get these so-called task trees, where the things that the robot should do is expressed as a tree. And since it's expressed as a tree, and we can express every task the robot does as a JPT, we can also express the entire plan as a probability distribution, and therefore make more interesting calculations on that than traditional machine learning. Then, of course, the thing that circuits do not use are transformations or change of variables formulas, because they in general destroy properties of integration. But we are also investigating that and under which conditions we can perhaps still integrate something. Then second to last thing is the convolutions of circuits. So if I have a random vector and sum it with another random vector, how would the distribution look like? And matrix for circuits, like, okay, I have this distribution for a robot plan, and here's another distribution for a robot plan. How similar are them? And that is a current ongoing bachelor thesis. Yeah, and then whatever the future will bring. So there are two implementations of JPTs right now. The one on the right is a production implementation that Daniel uses in his company because it's very fast, it's stable, and very fast. That's why it's very good in live applications. The GitHub link is behind the GitHub on the right, and left is, I would say, my implementation of it, but it's more a general circuit implementation of me that also is able to use the JPT algorithm to create a circuit. It has a unified interface and higher usability, but it's not as fast because it's written in plain Python, and Daniel has written his in Cython, so obviously there's a vast difference in speed. And the left GitHub link will lead you there. These are the most common references that are used in this kind of research. The first one is a foundation paper on when inference is tractable. The second one is actually a pretty good master thesis with very good visualizations on how to learn such things randomly. And the third one is a joint probability tree paper from Daniel, his wife, and me. Thank you for your attention. Are there any questions?